Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. This is the second video in the series on understanding resistance. In the first video, I covered the why behind resistance and resistivity. In this video, I want to talk about design-related stuff, like what happens when I have more than one resistor in a circuit. Where does the energy go? Resistive voltage dividers, and real-life resistors. When we have two or more resistors in parallel, then the total equivalent resistance is going to be less than the smallest resistor in the circuit. Well, why is that? Well, when we were talking about resistance being like a hallway in our first video, we had an apple pie down here at one end of a hallway, and we had a bunch of people up here wanting to get to that apple pie, and all these obstacles and collisions along the way impeding their ability to flow through this hallway to the apple pie and the cup of joe. Well, when we're talking about a parallel resistor, we now have a second hallway in parallel to the original hallway. And so this bunch of people up here are standing here looking to get to the apple pie. Some are going this way, but others are saying, wait, this is all bunched up. Maybe this will be faster. And so they're coming down the alternate route. As a result, more people get to the apple pie because now we have the same number going down this route. We have more people coming down this route. More people get here. The flow of people is higher. The number of people getting down here is higher. The same is true for our friends, the electrons, trying to get from one place to another through a network of parallel resistors. For some n number of resistors in parallel, the total resistance, what I'm going to call R sub t, may be found by this formula. And so, using this formula, you can calculate this total resistance, the total equivalent resistance. It's 1 divided by this blob down here, which is 1 divided by the resistance, the resistive value of R1, plus 1 divided by the resistive value of R2, plus ... keep going, R3, R4, R5, however many, up to your last resistor. So it's 1 divided by 1 over R1 plus 1 over R2 plus, and so on and so forth. But it gets a lot simpler if you only have two resistors in parallel. This formula turns into this. As simple as this. R1 times the value of R2, all divided by the sum of the two resistor values. It even gets simpler if you have a number of resistors in parallel that are all the same value, because then it is just the value of one of those equal value resistors divided by the total number of resistors. That makes it very easy. Because all of the resistors are in parallel, the voltage across any one resistor must be the same as every other resistor. So we have a conductor here, we have a conductor here, the resistors are in parallel, connected end to end. So the voltage across R1 must be equal to the voltage across R2, must be equal to the voltage across R3 through this whole combination all the way to R sub n. Now, on the other hand, if these resistors are different values and they have the same voltage across them, the current through any given resistor is not necessarily the same as other resistors in this parallel circuit. The current through any specific resistor, R sub n, may be found by this formula, which is the voltage that's applied, the voltage across the resistors in parallel, the voltage applied, divided by the particular resistance of the resistor in question. And so this is how you get the current through any given resistor. So now you know how to calculate the equivalent resistance of this. You know how to calculate the voltage across these resistors. It's just the voltage applied. And you also know how to calculate the current through any given resistor in this parallel circuit. Now let's take a look at series resistors. Series resistors. The more resistors you have in series, the higher the overall resistance is going to be. Now, if we go back to our hallway illustration, it's like having one hallway after another that the people have to pass through to get to our luscious apple pie. Each hallway has its own resistance to the flow of people. The hallway overall is indeed longer, and there may be more obstacles in one part of the hallway than there is another part of the hallway. The resistance to the flow of people to that luscious pie is greater because of the series nature of this. The same is true of our friends, the electrons. As they try to navigate from one place to another through the series of resistors, it's like this hallway. They have no alternate route. They are stuck with having to go through the resistors from one end to the other, just like these people. If they want to get to the apple pie, the only way they're going to get there is through the route that has been supplied. There's no escape. So for some N resistors in series, the total resistance, again, I'm going to call this R sub T, may be found by the following formula. Simple as this. We have R1, R2, R3, and so on to Rn in series. The equivalent resistance is R1 plus R2 plus R3 plus R4 all the way to R sub N. Now, the current, because remember what we said about the hallway, there's no escape, there's only one route to take. So this voltage applied, there's only one place, one route through these resistors. And because of that, we can say that the current through R1 must be, by definition, the same as the current through R2, must be, by definition, the same as the current through R3 must be, well, the same as the current through any one resistor. So if we say this is total current here, total current is the same as the current through any one resistor. But if these resistors are different values and the current through each individual resistor is the same, then the voltage across any particular resistor can't be the same as the other resistors if they're different values. And so in order to find the voltage across a given resistor, let's say voltage across R sub N, whichever resistor you want to call that, is equal to the applied voltage to the series string times the ratio of the value of that particular resistor and the total resistance of the string. So now you know how to calculate the total resistance of a series resistance circuit, R1 plus R2 plus R3 plus Rn. You know that the current through any given resistor in this series string must be exactly the same as the current through any other resistor in the series string. And you can calculate the voltage across any given resistor in that string by using this formula, V applied times the resistor in question divided by the total resistance. The act of resisting the flow of electrons means that our resistive material must be absorbing some of the energy of the electrons entering the material. So where does the energy go to that is lost in these collisions? According to the law of the conservation of mass and energy, it has to go somewhere. For the most part, it is expended in heat. That is why resistors heat up when they do their thing. Heat is expressed in terms of the power dissipation of the resistor, and it's expressed in watts. When selecting a resistor for any given application, you must first calculate the power having to be dissipated by the resistor, worst case now, and then you select a resistor whose rated power dissipation is no less than twice this value. According to Ohm's law, you can calculate the power to be dissipated by the resistor using one of these formulas. The first one is the voltage that is applied, or the voltage that appears across the resistor in question. You square that value and then you divide it by the resistance value. This will come out voltage in volts, resistance in ohms, comes out in power dissipated by the resistor in watts. The second one is the current that will be passing through the resistor. You take that value in amps and you square that value, you multiply it by the resistance in ohms, and you get the power dissipation in watts. The last one is the current that you expect to go through the resistor times the voltage applied across the resistor will also give you the power dissipation in watts. And again, once you calculate that value, when you select a resistor for that particular place in your circuit, you want to select a resistor that is at least twice that value in order to get the best longevity out of the resistor. You know, it's surprising how many times we run into voltage dividers in electronics designs. Because this invades so many places, I thought it wise to spend a little bit of time talking about it. The basic voltage divider is just a couple of resistors in series across some voltage source like a battery. So we have the voltage source, we have our two resistors in series, and we're looking at the voltage output, which would be the voltage across one of the two resistors that's in series. And to find the voltage output here is very simple. It's very straightforward. You have the voltage output, this voltage here, is equal to the voltage that you're applying over this entire string, times the output resistance divided by the sum of these two resistors, R out plus R in. But, and there's a big but here that you have to keep in mind when you're dealing with voltage dividers like this. In the real world, we don't have this V out coming out to some perfect high resistance load that isn't going to make any differences. The reality is that this is going out to some kind of device out here which has some finite resistance inside it. And so the real R out that you need to use in this equation is really this R out over here in parallel with the R in of our box here. And so the real R out, this is this entire thing here. So you have R out, I'm going to call this R in prime so we don't get confused with that one. R out times R in prime divided by R out plus Rn prime. Remember, this is a parallel resistor combination. And you take this value here and stick it in here for R out in order to find the real output. Now, if this value is many times greater than this value, you probably don't have to worry about it. But if, on the other hand, there's a possibility that this value might be small enough to make a difference, then yeah, you kind of have to include that into it. So there you go. Voltage dividers, you're going to find them everywhere, and it's really handy to be able to make this calculation. Lastly, I want to talk about real-world resistors. Real-world resistors need some sort of method of connecting to the outside world, and this is done through some sort of conductor, maybe like a wire or other such thing. And every conductor, no matter how big or small it is, has some inductance associated with it. So every resistor has some amount of inductance associated with it. Furthermore, we have these conductive connections to the resistor connected to the semi-insulator of the resistor. Two conductors separated by an insulator constitutes a capacitor. Thus, every resistor has some sort of capacitance associated with it. We roll this all together in the resistor model, which looks something like this. We have the lead inductances, we have the ideal resistor, and then we have the parasitic capacitance. Now, wire-wound resistors are nothing more than an inductor wound with resistive wire. So here I have some 75 ohm 10 watt wire wound resistors that I put on my vector network analyzer. The inductance of that resistor was 3.4 microhenries, and its resistance, as I discovered, was highly frequency dependent. At 1 megahertz, my 75 ohm wire wound resistor came out with 74.5 ohms plus the reactive portion of 21 ohms. So the actual impedance of my 75 ohm wire wound resistor at 1 megahertz was about 77.4 ohms. Now, I increased it to 30 megahertz, and now the real part is 108 ohms plus the effect of the inductance. We end up with an impedance of my wire wound resistor at 30 megahertz of 649 ohms. Oh goodness. Now you'll learn in the videos on inductance that inductance in parallel act is the same as resistors in parallel. So if you have to lower the inductance in a resistive something, one way that you can do that is by taking several resistive somethings. Let's say you want a 50 ohm resistor, and you have to connect from this point to this point, requiring leads that are a particular length. Well, what if instead of using a single 50 ohm resistor, giving you the inductance of this lead and inductance of this lead and the resistance of the resistor, what if we did one of these? Now we have 4 200 ohm resistors. Each one has the same amount of inductance associated with its leads. In parallel, we have 50 ohms because we have 4 200 ohm resistors. And then the inductance of these leads is now in parallel with one another, also dividing that inductance down. And so you end up with a much lower inductance 50 ohm resistor this way. Now I did a hack-a-day experiment in the shop, and yeah, I was able to prove to myself that this indeed does work. Now I didn't get 1/4 the inductance, but I did get a significant reduction in the inductance. So that's pretty cool. Well, now you have everything that there is to do with resistors design stuff. Thanks for watching. Toodaloots.